Hello, everyone. Welcome to the EasyPower Thursday webinar series. My name is Jim Chastain. I'm your host for today's session. We have with us two esteemed guest presenters from ABB and discussing a widely anticipated change in status of an NFPA standard. Before we get started, I wanted to touch on a couple housekeeping notes. There will be a copy of the video recording of the presentation posted to the website, along with a PDF copy of the slides, and you'll all receive a notice from EasyPower via email when that's available. If you'd like to enter questions for the presenters during the session, please use the question section of the webinar control system. And then we will be sending out attendance certificates for everyone that's attending the webinar today. And as we're in the habit of doing, we'd like to start off with a couple poll questions to get some feedback from the audience, and we appreciate your participation. First question is, are you familiar with NFPA 70B? Again, no liability or commitment here, just trying to get some feedback so our presenters know the makeup of the audience. We're expecting a fairly heavy attendance today, and I think the topic is very attractive. So it looks like we have a quorum. Thank you for participating. Here's how folks have weighed in on this. Looks like we have the right audience as far as needing some information on the topic. So good place to be. And the second question is, do you specify or purchase asset health monitoring sensors to drive better maintenance practices? Again, just trying to get a feel for where people stand on these responsibilities. Looks like we have fairly heavy attendance today in anticipation of this discussion. So we're close to a quorum. Let's see how folks have weighed in. Thank you for your input. Again, a good distribution of people with a need. And then the last question, do you factor in total cost of ownership in product recommendations or purchasing decisions? This will give our presenters a perspective on the audience understanding of the discussion. Okay. So here folks have weighed in on this one. Interesting. Excellent. Okay, at this point in time, I'd like to hand the controls over to Marcelo Valdez and let him do the introductions. Excellent.
Okay, sorry about that. This is Marcelo Valdez speaking. Thank you very much for attending. I hope that this presentation is useful to you. And I want to also take a moment to thank EasyPower for giving Harsh and myself the opportunity to speak to you about this important topic. Okay, as a bit of background, I was with General Electric 41 years before I joined ABB in 2018. So I've been quite a few years in the industry, so field engineer, sales, application engineer, so on and so forth. I work on a lot of standards, IEEE standards and others. Specifically, I am a member of the committee responsible for 70B. I'm also in the National Electrical Code Committee. It's important to note that whatever I say here is my opinion and does not represent an official interpretation or representation of interpretation of the standard by NFPA. What you're hearing is just me. Dr. Harsh Karandikar is a mechanical engineer, a global product manager with ABB, has significant expertise in equipment designs and similar, particular medium voltage equipment. And I think you will find this part of the presentation quite interesting. The agenda is to talk about 70B a little bit. Obviously, in this brief amount of time, we can't cover a lot of detail, but hopefully I'll hit on some high notes that are important for you to sort of understand the value and importance of this standard within our industry. And Dr. Karandikar later on will talk a little bit about maintenance planning, asset management, so on and so forth. Sort of one leads into the other. So what do we have? 70B is one of the 3 NFPA standards that are very, very important in our industry. Obviously, everybody's familiar with the National Electrical Code, which is derived from NFPA 70E. It may be slightly different in one jurisdiction, one state, one city, one county versus another, either because a different edition has been accepted or because there are local changes. I worked for many years around the city of San Francisco, and San Francisco likes to do things their own way, as does New York City and other large metropolitan areas. But then the National Electrical Code is the installation standard for the electrical industry in our industry. 70E has been in the news certainly quite a bit for the last 20 years and more, particularly since arc flash was sort of became part of the everyday lexicon in our industry, and it's a key standard driving safety practices in the workplace. 70E mentions 70B. It refers to it particularly in the second chapter, and hence doing the proper maintenance is very, very key to safety. And these 3 standards really define how to have and how to operate and how to maintain a safer electrical infrastructure installation. The document has been around for quite a few years, but it's always been a guide. And whatever level of attention it has received in the past, the intent of the NFPA by changing it to a standard is to increase that level of standard and really bring it into a par to the National Electrical Code and 70E. So it is now a standard. It is prescriptive language. It does say thou shalt do that, not that you should, you could, you might be. No, it flat out says you shall do that. Because of that, the standard, the content, if you're familiar with previous versions, is quite a bit different from previous versions. When you write a standard versus a guide or a recommended practice, you kind of need to focus on the minimum requirements that everybody agrees with. These are consensus standards. So when people sit in a bunch of room and they have to come into agreement on what the content is or will be. And the key is this becomes sort of a minimum definition of what you need to do. You can always do more. That's an important concept. Just like the National Electrical Code tells you how to design safely, not necessarily how to design or install well. You can install better than the National Electrical Code minimums. When it comes to safety, kind of the same thing. So a big question that comes up in conversations is, because it's now a standard, has it changed to become mandatory? I'm not sure I can give you the answer to that. I am not a lawyer, and I think this is probably more legal than a technical question. As mentioned, these 3 standards are part of what essentially supports OSHA. OSHA is the law. It is a law to drive safety in the workplace. So whether OSHA needs to be followed or not, it's really not quite as debatable. But how these 3 standards support OSHA might to some degree be debatable. National Electrical Code, of course, is mandated typically by local codes and laws, so on and so forth. But 70B and 70E are not strictly mandated, but they are referenced by OSHA. And that gives them, shall we say, a certain weight. So the reality is that safety in a facility is probably achieved via proper installation practices, proper procedure, maintenance procedures, operational procedures, and proper maintenance practices. And the US, at the end of the day, is a very litigious system. So you need to decide how strictly you follow this, how you refer to it when you write your maintenance plans and your procedures, so on and so forth. But generally speaking, I think it can be safely assumed that ignoring it is probably not an option. When you read the language in the standard, one of the things that it says fairly early on, chapter 4, is that the equipment owner shall implement, document an overall electrical maintenance plan, abbreviated here as EMP, that directs activity appropriate to the safety and operational risk, with a very key emphasis on safety. There must be some sort of documented plan that tells you how you plan to maintain your equipment, that you can then document that you are maintaining per that plan. Doesn't tell you what the plan needs to contain or is, but that you must have one. And it must be appropriate to address safety risks. At the end of the day, if something should happen, and now you need to point out how you at least attempted to prevent that something from happening, having documented maintenance plan and documented records that you stuck to that plan, and documentation that that plan was logical, followed applicable standards and guidelines, is probably a good idea. The purpose of the document is to provide for the practical safeguarding of persons, property, and processes from the risk associated with failure, breakdown, or malfunction, and a means to establish a condition of maintenance of electrical equipment and systems for safety and reliability. And there's an implication that a system that runs reliably is a system that is probably more towards safe than a system that does not run reliably. Reliability of your infrastructure in a factory or whatever is to some degree a business decision. Safety, not so much. It is more of a requirement. When you look at safety, you have to understand that that maintenance, proper maintenance, is in fact a risk control and a part of probably many other risk controls. When you do a risk analysis for a task or an operation where people may be exposed to a hazard, you need to estimate the likelihood of occurrence and potential severity of injury or damage to health, paraphrasing the words in 70E. Well, the likelihood of an occurrence to some degree and the potential of severity of injury is potentially dependent on the condition of the equipment that is creating or hosting the hazard, so to speak. Hence, it further states that the electrical equipment operating condition and condition of maintenance needs to be taken into account in that so-called task risk assessment. And the reality is any risk control that depends on a mechanical, electronic, or a reaction by a protection mechanism on the protection provided by a barrier, on protection provided by an enclosure, to some degree, will depend on whether proper maintenance has been done on that hardware, whether the hardware is ready to do what it needs to do, when it needs to do it, for the reasons that it's supposed to do it. If that maintenance is to some degree suspect, the risk control itself is now suspect and essentially cannot be relied on. And if you look at the hierarchy of risk controls, you will see that many of your engineered solutions, particularly, will depend specifically on that. Impact of administrative controls, such as the use of an ERMS setting, i.e. the maintenance setting on a circuit breaker or relay or whatever else, will also depend on that maintenance. Even your PPE itself needs maintenance. The reality is that maintenance is just critical to safety and reliability, and there's very little one can do to get around that. At the end of the day, reliability of your system, how much you invest and how much you do to maintain a profitable operation is a business decision. But a maintenance plan to achieve greater safety is in fact a requirement based, assuming that you take this standard seriously and you take OSHA seriously. And the two are connected inextricably because reliable operations, machinery running well, is in fact also safer. It is, if the operations of machinery, electrical equipment becomes unpredictable, the safety expected from that same machinery is also unpredictable. When you look at maximizing safety for staff that operates or maintains an electrical infrastructure or machinery connected to concentrated high energy, literally anything that can create a hazard and a risk for personnel, the things that you should be trying to do is to minimize exposure to that hazard, i.e., if the explosion is in the left side of the room, try to have your people on the right side of the room. Very similar to a joke about the doctor. When you go to the doctor and you tell him it hurts when you raise your arm, say, well, then just don't raise your arm. So if there's a hazard, why are you near it? What can you do to minimize that exposure? Then if you have to have exposure, how do you minimize the possibility of an incident? We all know some of those traditional solutions: high resistance grounding, impedance grounding versus solid grounding, keeping barriers away between energized conductors and a person working nearby so they cannot drop a tool, touch an elbow, or do something that creates an incident, even if they're not actually working on those energized conductors, they're just simply close to them. And of course, what most people talk about when you talk about arc flash, for example, is how fast, how sensitive is your protection, your relay, your circuit breaker, your fuse. Is it appropriate? Is it optimized to minimize the energy that the person, the human, will be subjected to if he is exposed and if the incident actually has happened? Like the hierarchy of risk solutions, I would suggest that this itself is a hierarchy. If you can minimize the exposure to zero, the other two don't really matter very much. If you expose it to a low number, well, then the other two matter to an extent. But the better you do minimizing exposure, the less important minimizing probability might be. And if you minimize exposure and probability well, at some point the severity may be, in fact, what is called a residual risk or an acceptable risk. So there's different ways you can approach this. Exposure is distance, frequency barriers. We all kind of know what those things are. Incident probability, typically simplification of task, less exposure to energy, less opportunity for error, which goes to, if you're doing less maintenance that requires actually working on energized equipment, there's less opportunity for error. Not to mention that every time you touch equipment, there's a possibility for human error that sets up a future problem. So as much as maintenance is important, there may be some situations where too much maintenance is also a risk. You need to figure out what the right amount of maintenance is. And of course, severity is protection, which relies on the maintenance of whatever it is that's providing that protection. Talking about the standard itself. There are 10 chapters at the front, which are sort of general materials, followed by 28 chapters, which are specific for equipment types or application. I'm not going to go through the details of the 28 chapters because there's not enough time. But there's no rocket science in there. It's all, anybody that has electrical equipment and does maintenance reasonably well is familiar with this. There are lots of standards that provide much more detail than actually what these 28 chapters provide, the NEETER standards, and certainly your manufacturer's instructions. But the first chapters are important. There are also 13 appendices with some additional information. There's also new content that was not in the previous the discussion about pools, public pools, photovoltaic installations, wind installations, and electric vehicles. That's all new content. This is the first time that's been written in the standards, and anybody that's familiar with these subjects particularly, we need your input, and I'll mention this again in the presentation. The first chapters have administrations, reference publications, definition, general, blah, blah, blah. what a lot of people focus on is this maintenance interval. So let me talk a little bit about this. The text provides three sort of classifications for equipment based on condition, and then implies three different maintenance frequencies. Even the least frequent or maintenance, i.e. maintenance done on equipment that's in good shape, may seem like very frequent maintenance to some of you. But let's not panic. We have alternatives. At the end of the day, remember that business continuity and maintenance costs are not necessarily maintenance driving factors. The driving factors here are safety, but they will be, of course, important to you. And where alternatives come in is when you can install continuous monitoring or use predictive maintenance techniques based on manufacturer's recommendations, accepted industry practices. They're okay. And you can change maintenance intervals if you have a rational basis and good information to do that with. But again, the key issue is, are you controlling the risk to personnel and facility operations from failure of that equipment to operate as expected? To that, you need to assess things like the physical condition, the criticality, the operating environment. So you need to make up what is called an equipment condition assessment. And again, deviations from the maintenance frequency as described in table 9.2.2 is possible. But if you're going to decrease the frequency, you need to explain yourself. That reasoning needs to be documented, needs to be a part of the maintenance plan, and then needs to be rational. Again, think of it, if you're ever put in a position where you need to defend it, you need to have a defense. Again, I don't want to sound like a lawyer because I'm not a lawyer, but this, I think, is kind of common sense. Conditions of maintenance is defined in the standard, maybe a little bit general, a little vague, or maybe even a little ambiguous, but they do have definitions. There is a term use, there's a series of terms used where it's called serviceable, limited service, and non-serviceable. Serviceable essentially means the equipment is in good condition. A limited service means everything is not exactly as one would wish, but it's good enough for the moment, and there are things you can do. If it's non-serviceable, that's an issue. And normal operations, and certainly normal maintenance or normal activities around this may have to be changed because non-serviceable equipment presents a significant risk. Chapter 9 of this book provides a little bit of detail about this. So you have multiple classes of physical conditions, classes of environmental condition, and classes for criticality of the equipment. Physical conditions, you have condition 1, condition 2, and condition 3. Again, condition 1 means equipment basically is good. There's no reason to believe that this equipment requires any special reaction. Whatever your maintenance plan says to do about it on a normal schedule-free business is probably enough. Condition 2, you're seeing a change. Something may be needed that you need to do some maintenance, probably in the shorter term rather than the longer term. Condition 3, you have serious changes, and you probably need to change how you're doing, what you're doing, or the frequency with which you're doing it. Non-serviceable equipment, you have an imminent risk. Again, risk assessment, you need to figure out what to do to control that risk. Clearly, access by unqualified persons shall be restricted, and non-serviceable equipment needs to be flagged. This is very similar to language in 70E in section 130.8, subpart K. Non-conforming equipment requires that you need some sort of correction before you use it. These are These are serious situations you need to pay attention to. Again, since this is all about safety, you can have equipment that, even if it's not in the best of shape, does not present the risk. When people are planning maintenance, there is equipment that is run to failure, and you simply replace it when it fails. Well, clearly, when it fails, it should not be putting people at risk, or else you really should not be running it to failure. And criticality condition 3 indicates that a failure, it means it will pose a risk, and you need to plan your maintenance accordingly. Operating environment condition 1 or 2 may be used when the equipment is used within its rated operational environment, i.e. indoor equipment in a relatively clean indoor environment. Outdoor equipment may be used outdoors, so on and so forth. But you need to be careful when something changes. For example, if equipment is designed to be run in an air conditioning room, air conditioning fails, and now everything's 120 degrees, that may not be the normal operating condition, and that may have impact of some sort that needs to be taken into account. There are tables that kind of help you understand all this. And I'm not going to go through this in detail, but there are tools within the standard to help you make these assessments. And I think part of the documentation of your decision making is to use these tools or other tools that are similar that your facility is more familiar with, but somehow you need to document that your decision making is rational, well planned, and using available information. You can modify maintenance intervals as mentioned. Certainly, if you're making it more frequently because of conditions, that's what you need to do. But it even gives you language about how you can extend your periods between maintenance. If you're basically doing your maintenance, checking your equipment, and never finding anything wrong, potentially you can lengthen the time between maintenance schedules. And the document actually does discuss that to some degree. Just as an example, when you're looking at dielectric materials, there is potential degradation over time. Your testing needs to be done so you detect the degradation, not so you go and do a test and then find out your insulation is just about failed. Because if it's just about failed, you probably waited a little too long to do that test. I'm not a maintenance expert. I'm not going to tell you how to do this. But when you talk to the people that understand the materials, so on and so forth, and familiar with maintenance, you need to keep this potential for failure over time in mind, and making sure that your maintenance is scheduled in a manner that you detect it before it becomes an issue. The equipment chapters, I'm not going to go through them in detail. They're organized similarly to try to keep the document consistent and easy to read. Again, there's not a lot of detail, and chances are if you're doing this, you're going to look to other documents to provide additional detail. But this gives you a framework to understand what you need to look at and what are the basics and minimal activities that you need to take into account. Mention new content. I'm, for example, responsible for getting public pools in, and I did that because of stuff that I heard at my National Electrical Code panel, and the inspectors telling me about the bad conditions of public pools, so on and so forth. But maintenance is not addressed in the National Electrical Code. We needed to find another home for it, and this was the home that we found. Solar installations, wind power, electric vehicle, that's all new stuff and growing. I have an electric car myself. But it's not a field that everybody is an expert in. So again, if you have knowledge, particularly in these areas, please read the document and send your input so the next edition is better. Summary for the section. This is a radical change in an old but important document. It's not perfect yet, probably never will be. More work is needed, more expert input is needed, particularly from users. So any of you that are users, that run your own facilities, that are familiar with maintenance in your own facility, you have any comments, complaints, suggested improvements, let us know. Send us public inputs for the next edition. We welcome them, and we will definitely pay attention to them. With that, I'm going to give the presentation over to Harsh, and I probably have taken up too much of my time. Harsh, it's all yours.
All right, I'm using my hotspot on my cell phone, and so hopefully this works and goes without a hitch. So as Marcelo covered, right, NFPA 70B is really talking about the requirement to have an electrical maintenance plan, an EMP. In this part of the webinar, that what I'm going to focus on is, it's one thing to have an electrical maintenance plan. Its second thing is to actually execute it. And there is, with the technologies that we have available today, it is possible to execute that plan with an eye towards optimizing kind of the total cost of ownership of the gear, and that's what I'm going to talk about. So we have sensing technologies, software, HMIs or tools that present data locally and remotely that can help us, improve the effectiveness of executing the plan and also optimizing the cost of executing that plan. So in terms of maintenance strategies, right, even today, maintenance essentially tends to be on a fixed schedule across the industry. It is still the standard protocol. That is, of course, an evolution from having basically to run the equipment to failure, right? There has been progress toward usage-based because we can monitor the equipment usage and the level of usage. And essentially, any plan is good as long as it promotes the safety, and as Marcelo mentioned, it is a rational plan. The trend, of course, is to move towards a condition-based and a predictive planning. Right? So when we talk about condition-based, it's basically a maintenance strategy that monitors the real-time condition of the equipment and then determines what the maintenance needs are. Right. So those real-time indicators could be any irregularities, trending information that shows signs of decreasing performance over time, or any other warnings of impending failures, right? So the goal really here is to monitor assets and then to spot impending failure. Predictive maintenance goes a little bit further. It takes information and data that you have as regards the condition of the equipment and uses algorithms, rules to process that data and make a prediction about what will happen to that equipment in the near future and the long term. And then use that information to able to basically create a maintenance plan. Right? So, as what we see today is there is basically availability of technology and tools that allow us now to get into this arena of condition-based maintenance and eventually predictive maintenance. So that gets us to asset management, right? That's really the goal of our maintenance planning. But what we would say is asset management, risk management, safety management, it all is kind of the same thing, right? The end result, it gets us all of this, right? It allows us to manage our assets, allows us to do it, minimize risk in the process, and also enhance safety. Okay. So, and the way that safety is improved, right? So it can be basically, firstly, improved by lowering exposure, right? If an exposure happens, it can be lowered, improved by lowering the probability of an incident. If an incident happens, it can be lower, safety can be enhanced by decreasing basically the energy released during an event, right? And all of these are impacted by good asset management practices when an electrical maintenance plan becomes the key. So if you do have failures, which can be a result of a maintenance plan that has not been implemented, or just where the end result of that implementation has not been good, the loss can be significant, right? So there's data from automotive industry, $1.2 million per hour, right? Airlines, a single incident is $150 million. So across the industry, right, whatever industry you work in, if you look at some of the available data, it is significant. And we have extensive literature, especially when it comes to switchgear. What are the kinds of things that have caused issues, right? Actually, a top thing among them is just loose connection of parts. Then you get to environmental conditions like humidity and dust, then human errors, incorrect work during maintenance. Then you get to faulty installations, right? Something that Marcelo covered earlier, right? So what is clear is that if the equipment is not properly maintained or operated, the consequences can be significant, not only from a safety standpoint, but also a financial standpoint. So that brings us to one of the key sort of technologies that can help us in our transition to a condition-based and a predictive maintenance is really the use of sensors, right? When I say sensors, it's basically any device that would convert a non-electrical input to an electrical signal that can then be processed, displayed, or converted to other information. On this chart, you will see basically there are a lot of different parameters that can be monitored, and when we specifically get into switchgear, what we have normally concerned ourselves with is temperature in the switchgear at key points, humidity inside the enclosure, presence of partial discharge, which is indicative of a breakdown of the insulation, and all manners of mechanical and electrical performance of a circuit breaker, right? So opening time, closing time, cumulative damage. So there are basically sensors available, right? And actually, we have multiple options of sensors for each of those parameters. Okay. So let's look at then, how a condition-based or a predictive maintenance program that should be part of your maintenance plan can help you minimize your total cost of ownership, right? And when we consider total cost of ownership or TCO, what we are looking at is our initial investment cost, right? Then the operating cost and the cost associated with maintenance, right? So what I'm going to do is I'm going to just show an example. So here's a lineup of switchgear, 15 kV, 3000 amp. It's a main time in configuration, right? Non-arc rest switchgear. We will look at different technologies that can be applied that help us with the condition-based and predictive maintenance. These are just samples of technologies. There are many others, but you could essentially follow the same principle to evaluate the effectiveness of those technologies to help you reduce the total cost of ownership. Right? So what I'll cover here is basically four things. So magnetically actuated breakers, current and voltage sensors, digital communication, and asset health monitoring. Okay. So if you look at magnetically actuated circuit breakers, right? So essentially, this is the technology that takes care of your spring mechanism, and it's a very simple mechanism. It has very minimal maintenance requirements. So typically a spring manufacturer's recommendation would be to maintain or service the mechanism every year, right? In case of a magnetically actuated breaker, we recommend nothing less than 5 years. So it's an extended period. So what we see is that if you use this technology, you would have a little bit of an increased upfront maintenance cost. One of the interesting side effects is when you look at the control power that is needed to supply for the operation of the breaker and to maintain the breaker state, a magnetic breaker actually requires less in terms of power consumption, so you can actually save on a battery system. So you would have some difference in the investment cost from an operating cost, right? It's more or less the same as a spring breaker, but the maintenance cost would be significantly less over the lifetime. Okay. Then look at another set of technologies. So current and voltage sensors are using digital communication, right? We have seen when you use these technologies, you can actually reduce the footprint of your switchgear, and not only that, you can massively reduce the amount of wiring that is involved. in that switchgear, right? And then you combine that with your digital communication technologies, you basically have total awareness of the state of your switchgear at any point in time. Okay. Again, what we have seen, so once you reduce your footprint, you're basically going to save on your upfront investment, the cost of the gear as well as the cost of building. The sensors typically have much less power consumption than instrument transformers. In fact, it is actually significant. So you would save operating costs there, right? And in terms of actual maintenance, that's neutral, but you do get significant safety advantages in using sensors, right? So you avoid problems like high voltages due to open CT secondaries. You avoid ferroresonance. So a lot of issues are avoided when using these technologies, right? Then finally, asset health monitoring. What we are concerned with here is monitoring the performance of the breaker or monitoring the condition of the switchgear. So bolt and joint temperatures, humidity, partial discharge. And then, like I said before, there are multiple technologies that are available, right? All are effective. It really depends on your preference on a specific application, okay? So again, when you use these technologies, so there is obviously an added upfront cost. But even if you can save, one kind of planned outage as part of integrating these sensors into your maintenance plan, that is kind of our estimate of what would be a savings, right? Plus, you can eliminate things like your annual thermography evaluation or even a PD evaluation that may be required every 5 years. So there are significant cost savings during the life cycle. Right, so if you look at the whole picture, and here kind of in column 1, basically what I've sketched out is what would be a manufacturer's recommended maintenance plan for a piece of switchgear with a breaker, right? Each installation would be different. A user may decide to do things differently, may make it more frequent or less frequent. But you can kind of take a snapshot of all the activities that are required over the life cycle of the gear. In this case, it was assumed to be 30 years. And then you end up with a overall cost savings, right? And then what we have seen is that using technologies that are available today, they are quite mature, right? So you may potentially get a small increase in upfront costs, but you're looking at up to a 50% reduction in lifetime costs, right? And this mainly comes through your execution of your maintenance plans. But more significantly, you are essentially contributing to create a safer environment. What a lot of these technologies do is they eliminate the need for the operating personnel to be anywhere close to the switchgear, right? Which is the most effective way of keeping them safe, right? Just keep them away from it if they don't need to be near it, okay? So I think that's just a quick overview. So we sort of covered, this transition to a standard as far as an NFPA 70B is concerned, where one of the key requirements is having electrical maintenance plan. And then we covered how we can use technology as part of that maintenance plan to kind of optimize the execution and essentially save you long term in terms of your total cost of ownership for that equipment. Thank you.
Dr. Harsh, we've got one question that came in regarding the analysis.
Yeah. So FMEA analysis, capturing information for these. So typically, from my experience, that is something you do upfront. So either it's part of the design of the gear or it's part of the creation of the maintenance plan, right? And of course, having access to this information, but then it is primarily historical information or trending information would contribute to that. So that, to me, it's kind of an input that would go into the selection of what you would like to do.
Marcel here, if I may, can you hear me?
Yes.
Yep.
Yeah, I see the question has to do with FMEA. In my slides, I believe that there's a mention of an article that I wrote several years ago, specifically using FMEA to look at safety investments, to try to rack and stack, pun intended, how to get the least bang for your buck, so to speak. So I would say that whenever you're doing a risk analysis of the impact of a failure or a failure, FMEA is a very important part. And I would suggest that the sensors properly located and algorithms putting together is information can help in that analysis. It certainly can help in preventing, sort of as a prevention through design type of technique, preventing exposure to hazards and greater risks. Thank you.
The question about the slides being available, we will make PDF copies downloadable when we post the video to the website. Everyone will receive a notice on that. That was an excellent presentation. We really appreciate you joining us today. I don't see any other questions coming in.
Yeah, needless to say, if anybody has any additional questions, please feel out to reach to Dr. Karandikar or myself. I'll probably put our email addresses on the PDF presentation, or I'm sure you can reach Jim and he knows how to find us.
Yes.
All right. Thank you.
Thank you very much. Thank you all for joining us. We'll hook up in a couple of weeks again. Thanks a lot.
Thank you.